All right, for this review question for the midterm, we're taking a look at something that should be familiar from the horsepower lab, right? So if you read through this question, you go, oh yeah, we did this. We're running up and down the stairs, determining the horsepower in our legs, right? Well, this one, you don't have to convert to horsepower. All the answers are in watts. A girl of mass 50 kilograms runs up a flight of 20 steps in 7 seconds. Each step is 25 centimeters high. What is the useful average output power provided by the girl to climb the flight of steps? So it's exactly the conclusions, that we kind of reached with the horsepower lab. If we're an open note test, you could just go back and say, oh, that's horsepower lab. Let me kind of review my calculations there to see how I would approach this. When I grade journals, sometimes I look at it and it's like, I can kind of follow the numbers that are there because I'm familiar with the lab, but I don't know if you'd be able to in the future. It's kind of just like, okay, I can see these numbers here, but they're not labeled. They're not, it's not clear. So your journal should be organized enough so it's helpful to you for the purpose of like, oh, I get an open note test. This is the horsepower lab labeled clearly with all the calculations that we did, and then it's going to be more useful to you. So if you're solving for power, it's good to kind of start with an equation for power. Power, remember, is work divided by time. You may have in your notes that power could also be thought of as like the average force times velocity. And that's because when we expand the definition of work, force times displacement, we know that displacement over time is velocity. So depending on the information that's given, it may be more useful sometimes to consider this or to consider this. I think for this one, it's best to just kind of think about, okay, we needed the power. Can we figure out the force required that this girl is providing to lift herself up the stairs? Can we determine the displacement? And it's kind of nice they just gave us the time. All right, so it says in 7 seconds. So we kind of like, okay, let's leave time, let's not like fold it into velocity. Let's leave it down here in the denominator so we can plug in 7 for that, right? Like given, unknown, equation, substitute, solve. Guess the answer. Remember that acronym? What's given, what's unknown, what equation relates those things, substitute the given information into your equation, solve for the unknown. Guess the answer. So 7 seconds is given. Okay, 50 kilograms is given. That's a mass. Is that the force? Like, how do we calculate the force? Does anybody know? Yeah, it's going to be the weight, right? So we said for the horsepower lab, the force that you have to apply to lift yourself up a flight of stairs is your weight, right? It is your weight. And we know the relationship between mass and weight, hopefully. So the force is mg, right? The force is the weight mg. We can assume this is here on Earth, okay, where g is 9.81 newtons per kilogram. The displacement. Does anybody know how we can determine the displacement? So 20 times 25, 0.25, right? Deal with that centi. Okay, if we look at all the units here are watts, a watt of power is a joule per second. A joule of work or energy is equal to a newton of force times a meter of displacement, right? A newton meter is a joule. A joule per second is a watt. So embedded within this unit watt is indeed the linear dimension meters, not centimeters. In other words, a joule is not a newton centimeter, it's a newton meter. So we do have to convert this into meters. And so a quick calculation of each step is 0.25 meters times all the 20 steps that the girl ran up gives you a net displacement of 5, right? I'm just going to leave this S for now. So everything here is just in general, the variables. Now we can start to substitute. So 50 kilograms times 9.81 newtons per kilogram, right? That's my mg force. The displacement is the product of the 20 steps times the distance per step, the height of each step. And so that's 5 meters, right? So just think about like where that comes from. And then divided by 7 seconds. So 50 times 9.81 gives you the weight. The weight times the displacement gives you the work, and the work divided by the time is the power. And I think when you crunch all those numbers together, you get 350. Another approach to this calculation is to say 2,500 watts divided by 746 watts per horsepower. You wanted to really get your, it's like, hey, we did a horsepower lab. 746 watts to a horse. Then this would be like 3.35 horsepower. And you might say, well, that's unreasonable that a girl would generate that much horsepower running up and downstairs. And you can maybe eliminate that as incorrect and say, well, these ones are too weak, you know, or too low in power. Only C seems reasonable. You could compare it to your own conclusion. Okay, and say like, oh yeah, I was going to answer like in the hundreds of watts, you know, not quite 1 horsepower, but like half a horsepower, something like that. And you say, okay, that's choice C. That's, you know, all these are reasonable values. My data resembled that. I ran a very similar thing. I think we did like up and down 12 steps. We did 24 steps, right? And your time might have been similar to that. So you could have used the conclusions there to say, hey, I have some familiarity with this, some experiential knowledge here that I could apply. I don't need to know the, you know, the physics here. I just have my experience of doing horsepower. There you go. Another worked example with Dr. Schleif. We'll see you next time.